So thanks to everyone for joining us today. We're going to be talking about landing the Perseverance rover on Mars. Our speaker today is Dr. Dave Way, and he works at NASA Langley in the Atmospheric Flight and Entry Systems branch. And he's been instrumental part of the Mars Science Lab landing and now the Mars 2020 landing that just recently occurred. So I'll leave the introductions brief and let Dave take over.
All right, thanks, Rick, and thanks everybody for having me today. I'll get my presentation up here, and here we go. Again, thanks for having me, and I think today is kind of an interesting day, timing-wise. Could be kind of a pivotal day for Mars exploration. We've said for very many years that the US has been the only country to successfully land on Mars, and in just a few hours, the Chinese will be making their first attempt. You know, I wish them well, and I know exactly what they're through because we just did it just a few months ago. I will start here with just this picture that's on my title art, and it's really one of my favorite pictures that came down after the landing, and this was taken during the sky crane, just mere moments away from touchdown, and so time is frozen in this image. And it's a very pregnant pause here right before we touch down. And of course, I think everyone online probably already knows the outcome, but we were all holding our breaths at this point. And also, before I get too far in, I want to say that landing on Mars is hard. It's not easy, and so I'll try to, explain a few of those things as we go along. When we get to the end, I want to make sure there's plenty of time for questions, and be glad to answer whatever questions everybody has. And so we call it the 7 minutes of terror. It takes about 7 minutes to get from the top of the atmosphere to safely on the surface. And here's a few of my teammates describing how it goes.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror, because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from a spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
It's the biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given it.
The science team identified Jezero Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
You look at Jezero, all you see is danger. How do we go to a site that we never thought was safe enough to go to before. So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. And once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. Its job, right, being the first leg of sample return to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
So that described a little bit about some of the challenges that we face during entry, descent, and landing. It is by far the most dangerous phase of any Mars mission. And NASA Langley has contributed significantly to the project, not just for the past 8 years, specifically for Mars 2020, but even going back as many as 20 years ago when we were just beginning the Mars Science Laboratory mission. And primarily, Langley's contributions are in 3 different areas. The first, I'll just lump together all of the aerosciences, but really it's 3 independent areas, both the aerodynamics that were led by Mark Schoenenberger, the aerothermodynamics, which is led by Carl Edquist, and the parachute performance, which was led by Juan Cruz. And all of that expertise was used to develop models of the aerodynamics for our simulations. And those models were informed by both computational fluid dynamics and also by experimentation were available. And just to kind of preview a little bit the outcome, these models were very successful and extremely accurate. And how we know that is from one of the other areas that Langley contributed heavily, and that was in the Mars Entry, Descent, and Landing Instrumentation, or MEDLI. We flew the first MEDLI sensor suite on MSL back in 2012. And so we repeated that work led by Henry Wright for the MEDLI 2 instrumentation. And you can see some of the instrumentation here on the heat shield. You can see the orange cabling, which is connecting some of the sensors to the sensor support electronics, or SSE box, which is kind of black and hard to see in the picture. But this instrumentation provided a gold mine of data on 2 flights now. And this is very critical for us in order to advance the state of the art and be able to take on these more challenging missions. It's so critical for us to be able to measure how we measure our performance and compare that back to our predictions, and take a real honest look at how well our models and simulations perform. And the third area is in flight mechanics and simulation, which is my discipline. And there we're tasked with bringing this all together, applying some physics that were developed more than 300 years ago with the latest in supercomputing resources available to us to try to predict the performance of the vehicle ahead of time. And I could probably spend the next hour just on this one chart. There's a lot here. And it's one of the fun things that I love most about flight mechanics is that we're really in the middle of the systems engineering team. And we interface with cognizant engineers from across the country at JPL, at Houston, at the Johnson Space Center, at Ames, and here at Langley. And we bring together the best models that we can of both the environment of Mars and of the vehicle itself so that we can assess the performance. And part of what makes it so challenging to do entry, descent, and landing is the problem itself. It's a very multidisciplinary problem. The subsystems are very tightly coupled. The design space, the physics are very nonlinear. We're very data poor in terms of we don't do these Mars landings every day, and so we don't have a very large database of historical data to go back through. And all of that contributes to making for a very difficult problem. And so it's very critical to the success of the mission to bring in the right expertise, you know, a good mix of early career and, you know, some of us that have earned our gray hair and scars that we carry with us, along with the best models. And that really is a balance in fidelity as well. It's the best model's not necessarily the one that's the highest fidelity. And so that could be a whole talk in and of itself. And if we get some time in the questions area, maybe we can go into that a little bit more. But you really need to find the right balance of fidelity of the models. And related to that, and a very similar concept, is that we need to provide the right amount of margin. We're dealing with extreme environments where in general we don't have a whole lot of margin. And margin is very critical. You can't run out of it. But at the same time, we can't be too heavy-handed in how we apply margin. Because of that tight coupling in the systems. If one system applies too much margin and makes their job much easier, they're going to be pushing that pain out to some of the other subdisciplines, making their job a little bit harder and potentially having those other subsystems take on a bit more risk. And ultimately, that's what it's all about, is being able to balance the risks, manage those risks so that we can give the vehicle the best chance of success as possible. So some of the key challenges for Mars 2020, again, I could go on probably for several years with all of the detail behind this, but the key design of the project, which started back in 2012, shortly after Mars Science Laboratory landed, was to do a build to print, a refly of another mission, using some of the available hardware that was built for MSL. And we would allow ourselves to fix a few things that didn't go quite right last time, or improve some robustness where we could use some. And to that extent, I think we did a pretty good job. As build to print missions go, this one was nearly as build to print as you can get. But there was some kind of key places where we took on some challenge, and primarily that boiled down to landing a bigger rover, a heavier rover, and in particular doing so at a much more dangerous landing site. And I'll talk more about that later. The other thing I will just mention briefly, but won't go into too much, because 2020 was a challenging year for all of us, and we're all getting pretty tired of talking about the pandemic. But you know, for us, 2020 was supposed to be a very big and exciting year. So much so that we put the year right there in our name, which in and of itself was a bit gutsy thing to do ahead of time. But like so many other people, we had to learn how to do our jobs, which amounted to landing a rover, how to do that from our dining room table. And another thing, and quite similar to folks, we had to give up a lot of things. You don't often get to, in a lifetime, go down and watch a launch in person that you worked for many years on, nor do you get to sit with your colleagues as you attempt a very dangerous entry, descent, and landing. And those are things that you really look forward to throughout the entire mission. And we had to do without those things this time. And so that made it a bit poignant and sad. But I will talk about a couple challenges in particular that we faced along the way. I think it may almost be said that no mission is complete until you've ripped up a parachute. And so maybe I would propose that in the future, we should have a very solemn ceremony at the beginning of the mission where we tear a parachute to shreds so that we don't have to do it in test. But as things would have it, a completely unrelated project was testing their parachutes. And this was in 2015, so about 3 years into our 8-year development. And it was a 50% bigger parachute, almost 2.5 times the area. It was a different design, and it was deployed at a higher Mach number. But let's see what happened. There was a balut deployed, and in a moment that's going to extract the main parachute, which is a very large 33.5 meter parachute. And there we have it. Not very pretty. And what that caused for us on Mars 2020 is, prior to this time, our intent was to fly a build-to-print parachute from Mars Science Laboratory. And we felt very comfortable in that. But now, after the failures of the LDSD project, it really caused a lot of questions to be asked in the community, caused a lot of concern in the community. And we found ourselves in a situation where we had a vote of no confidence on a parachute. And that resulted really in a lot of heated and very animated debates, even amongst the project. But the ultimate response of the project was to completely redesign the entire parachute decelerator system. We went to a heavier broadcloth, and that increased the mass by 50%, which had a lot of trickle down changes throughout the rest of the system. And we also reduced our flight limit load from 65,000 pounds down to 50,000 pounds. And we proceeded in flying 3 sounding rocket tests at supersonic speeds to qualify our system. So we made 3 flights of our exact parachute design in a relevant environment, stepping up from nominal conditions at about 34,000 pounds to near our flight limit load at 50,000 pounds. And the final flight was at 40% above our flight limit load at 70,000 pounds. And so that gave us the confidence that the parachute would work in flight. And here we have the video from the last of those 3 Aspire flights. So very quick, but a very symmetric inflation. And ultimately, all those heated arguments, everyone really all had the same objective in mind, is we wanted to ensure a safe opening of the parachute during entry, descent, and landing. And so this photo was taken from the HiRISE camera on Mars Reconnaissance Orbiter from about 435 miles away. And that is our flight parachute in action, inflated at Mars. And so we were very happy to see that, very happy that the system worked. And we were extremely happy in that we had ruggedized cameras on board the system. And for the very first time, we were able to watch the inflation of the parachute at Mars. And so that video, I'll play it again real quick, is actual video in flight at Mars. And there we have it. And as it would turn out, our parachute deploy conditions were right on the money. The opening load was very nominal. We gained a lot of experience during the Aspire flights. And we had a very symmetric and a very benign opening at Mars. And so all's well that ends well. One of the other largest challenges, I would say, for the project, though, really came down to the landing site. And we went through a very long process to choose the landing site. We chose the landing site based on where we felt we could get the most science. This was by far the most challenging and dangerous landing site that we've ever attempted a landing at Mars. This was Jezero Crater. This was a site that was known to us. Previous missions had been proposed for Mars Science Laboratory and rejected as being far too dangerous. And so I can tell you that this was the source of some sleepless nights and some gray hair and some nervousness. I honestly thought that if things didn't go well, that the image of this delta would just be burned on the back of my retinas, and I would be able to see it every time I closed my eyes. The edge of that delta is a 260-foot cliff, and that was right in the middle of our landing ellipse. We have inescapable hazards that we can't get out of, like the craters that you can see in and around the delta. There are sand traps, that the rover could get stuck in and not be able to traverse out of, that you can't quite see in this image. And there were rocks, very many rocks all around. A lot of very large rocks that we could see from orbit and identify, and a lot of smaller rocks that we couldn't see, but we knew that were there. On the image on the left is, has some false color to show the different kind of geologic terrain types, but the image on the right is part of a hazard map that we put together, where we assessed the safety of each pixel in the entire landing site. And you can see there's quite a bit of red, which is greater than a 5% hazard. And the areas that we were trying to land on are the blue areas that were the safest. And in order to do that, we had to take on a new system, which was the terrain relative navigation system. And again, I'll let a few of my colleagues explain what that system was about.
We are in Death Valley testing terrain relative navigation, the new technology for Mars 2020. The terrain in Death Valley is very much like Mars. It has a lot of sand dunes and steep slopes. It's quite similar to the landing site that Mars 2020 will be going to. We're taking a copy of the system that will be on the spacecraft, and we're testing it in the way that it would be used during the flight mission.
Terrain relative navigation gives the vehicle the ability to figure out where it is. This is kind of along the same lines of what the Apollo astronauts did with people in the loop back in the day. Those guys were looking out the window and looking for different craters and other features on the moon that they knew of from the maps we had of the moon. So that way they could figure out where they are and figure out where they needed to land to be safe. So for the first time here on Mars, we're automating that.
What terrain relative navigation gives you is the ability to avoid hazards that you already know about. So large hazards, hills, craters, things that you've seen before. With the camera, we take images as we're descending, and we match pieces of the image to orbital imagery that we have stored on board. And if we make many of these matches, we're able to figure out where we are relative to the map.
If we didn't have terrain relative navigation, the probability of landing safely at Jezero Crater is about 80 to 85%. But with Mars 2020, we can actually bring that probability of success of landing safely at Jezero Crater all the way up to 99% safe every single time.
We don't have an astronaut that we can put on board Mars 2020, but we can put this system, this terrain relative navigation system, so that the spacecraft can figure it out on its own.
I could see it being used on lunar missions, science missions, as well as human missions. Future Mars missions, of course, Mars sample return, Europa lander, landing on a comet, pretty much everywhere you want to land, you're going to want to have terrain relative navigation.
So this next video that I'll show real quick is that terrain relative navigation system actually working at Mars. The quadrant up in the upper right is the raw image and identifying the landmarks that are matched. On the bottom right, you see that image then projected on the onboard map. And the blue square is enlarged on the left side of the image. And so you'll see the different colors symbolizing the landmarks that are matched from each of the images. Green is good. Those are the ones that meet the correct thresholds and are used to estimate the position. If you see some blue, those are really good. That means those were good landmarks that were matched, but we matched so many landmarks that they were extra and weren't used. And so let me play this for you real quick. And this is terrain relative navigation in action at Mars. And there we go. And so what the lander vision system, which is a subset of the terrain relative navigation that's running those algorithms, was able to detect our position in flight. That position was very accurate. And had we continued on parachute, we would have landed somewhere in the region of the white plus that's shown in the middle of the two colorful wedges. Those two wedges are the search areas that we then searched to find the safest landing sites. We have the northern wedge was searched, and the best pixel in that northern wedge was that green pixel that's surrounded by, outlined in black. That's just on the other side of that very large crater. And that was a fairly safe pixel. It is a little bit close to that crater, and so we're likely to see in that area some ejecta from the crater impact. And so if you look then in the southern search region, the safest pixel was found way in the far corner of that search region, which is the green box highlighted in white. And based on our assessment of the hazards at that pixel, the southern pixel had about a 0.5% better success rate than the northern pixel. And so that's the one we chose. And we flew then to what would become Butler Landing. And that brings us kind of back to my favorite image, which takes us right at those moments just before touchdown. And we're landing now in the exact spot where we're going to come down. And this spot is within about 5 meters of the center of that pixel that we were talking about. So the overall accuracy of the TRN system was very good. And we'll now watch how it all unfolded.
Propulsion, go. EDL phase lead, go.
We have deemed Perseverance ready to execute entry, descent, and landing on her own.
Confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second, about 120 kilometers from the surface of Mars. It will start controlling its path to the landing target. Parachute has deployed and we are seeing significant deceleration. The heat shield has been separated. Perseverance now has radar lock on the ground. The back shell has separated. Skycam maneuver has started, about 20 meters off the surface.
Tango Delta, nominal.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
And so here is some shots of many of the team members shortly after touchdown. And so, you know, it's easy, I think, for people to understand and kind of get caught up in the emotion of the event. But for those of us on the project that have invested 8 years in this, it's really hard to describe just how truly scary it is when you have that much of your career on the line. But this is this is the end result. This is what we're after. This is boots on the ground. This is an image of our landing site. And so you can see the kind of lighter toned areas where the plumes from the rockets dug out some dirt during the landing. You can see that delta cliff face on the horizon. And in the near vicinity here, there aren't very many large rocks. And so we really did pick a very safe place to come down. TRN was instrumental in selecting that place. And we really could not have safely landed at Jezero without all of that. Really the part of the landing which stands out the most to me is just the fantastic video that we were able to capture with the EDL cameras. It's the first time that we've been able to put these ruggedized commercial off-the-shelf cameras on the descent stage looking down at the rover, on the rover looking up at the descent stage. We had 3 cameras looking up at the parachute during its deployment, and 1 on the rover looking down. And so really for the first time ever, we've been able to watch what it looks like to land on Mars as the landing is actually happening. And so I could watch those videos for hours. There's a lot of great information there. And lastly, I just want to say that these things don't land themselves. Well, technically they do land themselves, but it really takes the people involved in the project, the engineers, the scientists, the technicians, everyone from the initial designs to building, assembly and test, operating the vehicle. It takes a lot of people. It takes a lot of hard work. Landing on Mars is hard. But now we're very excited because we've now put the rover in the place. The search for life on Mars is underway. The very long-awaited start of Mars sample return. The first leg of Mars sample return is now on the surface of Mars, ready to collect samples. And we can come now bring those samples back to Earth. And so with that, that's the end of my prepared material. And I'd be glad to take your questions.
Well, thank you very much, Dave. That's quite an accomplishment, and that video is quite amazing. I was blown away by that as it came in. It's high definition video from Mars. It's amazing. So we have one question right now: is how do you prepare for an unknown hazard while landing? And that came up during the TRN discussion. So
yeah, that's a great question, and it's a difficult thing to do, and something that we actually spent a lot of time working on and struggling with in a bit, particularly in trying to understand what the risk was of the smaller rocks that were too small for us to see from orbit, because they could still be dangerous. Rocks in that size that are too small to see from orbit could still be too large for us to land on. And so we had to rely on some statistical methods that help predict what's the probability of seeing a small rock, given the number of large rocks that are in the same area. And we had many a debate along those lines on, how do we know this? Can we believe these models? We're putting a lot of faith in them. And ultimately, the real key to that process was in being able to apply a little bit of standoff distance, so that the system would always try to come down as far away from all of the hazards as possible. And even in trying to estimate these small rocks, there were still enough safe areas around that we could be very confident in our landing, as long as the system worked, and that was the key. We were putting a lot of faith in a system that had never been used before.
Another one just came in and says, what technology is most needed to extrapolate to the target of 20 metric tons on the surface? I'm assuming this is human landings they're talking about.
You know, I don't think you could say one technology is going to get us there. That's a order of magnitude increase, and then times 2 over what we're doing now, and really we're seeing now with the next follow-on missions to Mars for Mars sample return. We're going to be stretching the limits of our current technologies. So we're going to have to start incrementally kind of stepping that up a little bit. But it is a very large jump to get to that 20-ton kinds of limits.
As a follow-on, you didn't talk too much about the sky crane maneuver. Maybe you could talk a little bit about the limit of that kind of system.
Yeah, the sky cranes has worked very well for us. It has some very nice features to it. One of the ones that I love the most, I love to say, is the images that you see of the rover after it's driven away from the initial landing site, and looking back at the landing site, you see these tire tracks that just appear. They just start out of nowhere. And the rest of the time that rover is on Mars, it will be driving around and it'll be leaving tracks behind it. But the tracks just start. And there's nothing else in that area. So literally we're able to land this rover on its wheels, ready to do science. And you know, the surface team is a lot more cautious because they have plenty of time. You know, we fire 70 something pyros in 7 minutes, and they'll spend the next like week raising the arm and turning the wheels for the first time. But you know, if they were faster, that rover could be ready to start roving in a very short time. Other than that, it scales pretty well. It's propulsive. The descent is not, by design, is not that fuel efficient. But you know, we spent fuel to get rid of other uncertainties like terrain variation, and to give us time to execute different parts of it. So I think that general design of the sky crane does scale up, and I think you could use that.
Okay. We have a question along the TRN system. It says, did the TRN system algorithm decide that the north site may have had a ejecta from the nearby crater, or was that somehow a human observation / decision at some time before the landing? And I guess maybe kind of generalize, you know, how do they come up with some of these maps? How much human interaction is needed?
Yeah, and that's a great question. We could probably spend an entire hour talking about the maps and how they were generated. And there was a lot of effort that went into them, both some machine learning algorithms to help do things like rock detections, but also a lot of human labor. All of the inescapable hazards that we identified, which could either be craters that are too steep to get out of, or sand dunes that the rover drivers were uncomfortable driving through. All of those areas were identified by humans looking at the map. In addition to that, all of the automatic rock detections were then also looked at by humans in the safest areas of the landing of the hazard map that we were that we were landing on in our simulation. So we knew the areas of the system like to go to where they had the highest probability within the allowable search areas. And we had humans review 100% of those areas. And so there was a lot of human involvement. All of that really gets boiled down to a number that's given to a pixel that's on a map that the machine in flight then looks at. And so literally the algorithm on board is scanning this map that we've put a lot of care in generating. It's scanning each of the pixels and it takes the maximum one, whatever the maximum number was. And so there wasn't a conscious decision about the ejected in that area, but I was making a point earlier that's why that area, even though it looked pretty flat, was likely rated a little bit more hazardous in the actual map.
Can you speak to how good the simulation was at picking the point that the TRN actually did pick in flight?
Yeah, I'd be happy to. I love talking about the simulation. In particular, I love when the mission is successful and you're able to go back and then look at the telemetry and compare that back to your pre-flight predictions, because that's really how we learn. And in this respect, the simulation did very good. If I had to grade it, I would give it an A+. It was not a perfect score. There were a few things that we are still looking into and a few things we can still learn from. But in terms of the landing location, we landed about on the edge of about a 1 sigma ellipse. And so that was pretty near the center. And I think that in our 8,000 case Monte Carlo pre-flight, that about 50 of them landed or chose that same pixel that we chose in flight. And having a high number like that really is reflective of the fact that the place that we were coming down was a rough area and not really one of the best areas in the ellipse to be coming down from a surface safety perspective. And so the system did its best in finding, given what was available to it, the safest site to land at.
Great. We have a parachute question. It says, did the parachute redesign mass increase result in loss of planned experiment or instrumentation?
That's a good question. No, it didn't. We didn't have to throw anything off. Part of that is the mass of the MSL and the Mars 2020 systems is getting on the large side at around 3.5 tons at entry. And so, even 50 kilos, which is a lot of mass, makes a pretty small percentage change in our entry mass. And we had a lot of performance to give. The system has a lot of altitude performance, and we were assisted in the year 2020 being a very good Mars opportunity, a very good Mars year for landing at Mars. We were very near the top of the pressure cycle at Mars, and so we picked up probably about 1.5 kilometers of altitude performance over the MSL design, based just on the increased pressure for this opportunity. We lost some of that back because of mass, but we're still able to maintain plenty of timeline margins in the EDL timeline.
Here's one more question. It says, is NASA testing any other landing methods after bouncing airbags and landing via a tether?
So there are lots of ideas that are being kicked around for future missions. I think a lot of the so we've demonstrated 3 basic variants: the airbags that you mentioned, legged landers, which we've used several times now, twice in Viking and twice for Phoenix and Insight. 3 airbags for Mars Pathfinder and the 2 MER rovers, and now 2 sky crane landings. And so the airbag system does not scale very well above the MER class rover size, which is what drove us to develop the sky crane from Mars Science Laboratory. And so most of the designs that you see going forward are either sky crane type systems or legged type landers to get us to the surface under propulsion.
Okay. There's one more about the parachute testing that was done, and it's about what altitudes those parachute tests have to be done at the Earth atmosphere, kind of to simulate the Mars conditions.
Yeah, that's a great question, and it speaks right to some of the challenges. Is that with a system that's designed to operate at Mars, it's extremely challenging to find the right relevant conditions on Earth in order to test those systems, as we intend to fly them when we get to Mars. And particular with Mars, the atmosphere being about roughly 1% that of Earth's, we have to go up to about 100,000 feet in Earth's atmosphere to get to an equivalent pressure. And in order to get the right flow field, we deploy these parachutes supersonically for us at about Mach 1.75. Other missions that looked at pushing that up closer to Mach 2. So you have to get the vehicle up to those kinds of speeds at extremely high altitudes on Earth. And it's been done typically in one of 2 ways, which is either a weather balloon kind of launch, which is what the Low Density Supersonic Decelerator, or LDSD project did, and then a rocket from there to get you up to speed. Or as we did for the Aspire flight tests, which were conducted here on the eastern shore of Virginia at the Wallops facility, as we put the parachute on a sounding rocket and then use that to get us up to the 100,000 foot kind of altitude range. But it's very challenging.
Mm-hmm. And one last question. What do you, I guess your opinion, you think has been the biggest change since the days of Viking in terms of Mars missions?
Biggest change? I think for us, and I was always very thankful of this, for both Mars Science Laboratory and for Mars 2020, is we had the benefit of all that previous knowledge, way more than the Viking system had when they landed. And we had the extra benefit of these orbiters in orbit, detailed maps of our landing site. We had a 1 meter by 1 meter digital elevation map of our entire landing site, a landing ellipse plus some. And we had identified rocks, individual rocks down to on the meter, about 1 meter in size, maybe 1.5 meters, again, throughout the entire landing site. So the level of knowledge of our eventual landing site that we had far exceeded anything that the Viking folks had. And so they were really venturing out kind of into the unknown a lot more than we were. And so I think that's been the biggest change. in the development is just that improved knowledge that we have.
Okay, great. Well, thanks to everyone for joining and the great questions. And thank you, Dave, for hosting this. This has been very enlightening talk. Just a note to everyone, this is being recorded and will be posted so you can share, and hope more people can see it. So thank you again, and have a good day.
So thanks, everybody. Thanks for having me.